Hey again, everyone. In this video, I'm going to be going over the solutions to the 6th FRQ practice problem. If this one looks familiar to you, that's because this was actually the question that I gave you as part of the test on Unit 4. So if you had trouble with it the first time around, hopefully you were able to make a bit more sense of it this time and make some more progress on it. So in this problem, we're looking at a cart that is traveling along this roller coaster that has a large drop, and then it goes through a vertical loop at the end. And there are two key ideas that we're going to use to analyze this problem. One is called the conservation of energy. That basically says that the mechanical energy of the cart Earth system is conserved. Since there's no friction here, there's no energy being dissipated as thermal energy, so we only have two types of energy to deal with, which are gravitational potential energy and kinetic energy. And though the amount of each of those quantities may change throughout the motion of the cart, the sum of those two forms of energy will remain constant. So that means we can say, for instance, if we look at the cart at two different points, A and B, we can say that at point A, the total energy will be gravitational potential energy, mg times h, the height at A, and the kinetic energy will be 1/2 m times the velocity at A squared. And if we add those two together, that's going to be equal to the total energy that we have at point B, which will be mg times the height of point B plus 1/2 m times the velocity at B squared. And we'll actually use this formula later on in the problem. The other idea here is uniform circular motion. Technically, when the cart goes through this vertical loop, it is not undergoing uniform circular motion because the speed does change. But at the instant when it's at the top of the loop, we can still use one of the results relevant to uniform circular motion, which is that an object traveling in a circular path will experience a force directed towards the center of that path. That's what we call the centripetal force. And if it's undergoing uniform circular motion, then the net force will be that centripetal force, which is the mass of the object times v squared divided by r. All right, so let's go on and look at some of the problems here. So part A asks us first to indicate on the figure the point where the maximum speed of the car is attained. So when the car is going through this loop, it's going to speed up and slow down at various points. The basic idea here is anytime it's going downhill, it's going to speed up. Anytime it's going uphill, it's going to slow down. The reason is, as it's going downhill, it is going to lose gravitational potential energy, or we should say the gravitational potential energy of the cart Earth system will decrease, and that's going to result in an increase in the kinetic energy of the system. So the point where we have the maximum speed, that's the maximum kinetic energy, that's going to be where we have the minimum gravitational potential energy of the cart Earth system, and that happens when the cart is at the lowest point of the track. So the answer to part 1 is going to be for us to draw point P right here. The second part, they asks us to actually calculate that speed. All right, so I'm going to use a modified version of the equation that I wrote up above. At point A, the gravitational potential energy will be mg times the height at A. The kinetic energy at A will be given by this formula, and then we can set that equal to the sum of the gravitational potential energy and kinetic energy at point P. All right, so some of these terms are going to be 0. We're told the cart starts from rest at point A, so VA is 0, which wipes out this entire term. At point P, let's just say we're going to measure the height from the dashed line along the bottom of the figure, so HP is also going to be 0, which makes this entire term 0. So our equation is actually a little bit simpler. It's just this. And we can cancel the mass of the cart from both sides, and now let's move the 1/2 over to the other side and plug in some numbers. So let's just use use 10 for G. The height at point A is 90 meters, and that's going to equal VP squared. So if we plug in the numbers, velocity at point P comes out to be roughly 28 meters per second. All right, so that is part A. Part B wants us to calculate the speed at point B. This is going to be done exactly the same way. We're just going to use B instead of P on the right-hand side of the equation. So here's our potential energy at A again. I'll go ahead and leave out the second term because we know the kinetic energy is 0 at A. At point B, we're going to have some gravitational potential energy and also some kinetic energy. All right, so what can we do here? The mass will cancel all three terms once again. Let's plug in G equals 10, HA equals 90. HB, if we look at the figure here, that is 50 meters above our reference point. And then we have our kinetic energy with the mass canceled out. All right, so if we work this out, we get 900 equals 500 plus 1/2 VB squared. That means 1/2 VB squared must be 400. VB is going to be the square root of 800, which is about, what is that? Oh, I'm sorry, I had the wrong answer here. This is actually about 28 meters per second. This number up here is actually more like 42 meters per second. Apologies for that. All right, so now we have the correct speed of the carts at those 2 points of interest. All right, so now at point C, we want to start thinking about forces. Up until this point, we've just been using energy considerations to calculate the speeds. At point C, we want to think about what's happening to the cart when it is upside down at point B. So they give us this little diagram of the cart. You want to imagine the track is actually going to be here above the cart when it's at this particular part of the track. So what are the forces that are going to be acting on the cart? Well, there's going to be a gravitational force, which is always straight down. We call that mg. There's also going to be a normal force exerted on the cart by the track. Since the track is above the cart, the normal force has to be downward. So these are our two forces. Both of them point in the downward direction. So this is the first part of part C. The second part asks us to calculate the magnitude of each of those forces. Well, the gravitational force we can get pretty easily because we're given m is 700 kilograms. So this is going to be about 7,000 newtons. But what is the normal force? So to get that, we're going to have to use the other key result that I mentioned up at the beginning, and that is the net force on the cart when it's at point B must point towards the center, which is downward in this case, and it's got to be equal to mv squared over r. Okay, so let's write that out. So v is what we called VB, and r is the radius of the loop. So the mass is 700 kilograms. VB squared, if we look at our results for part B, that was 800. And then the radius of this loop is 20 meters. All right, so let's see, we can cancel a factor of 10 here. We can actually cancel a factor of 2. Also, this becomes 40. So this simplifies down to about 28,000 newtons. So the net force must be 28,000 newtons straight down. We have 7,000 newtons from the gravitational force, so the normal force must be whatever is left over. So the net force is equal to mg plus the normal force, since they both point in the same direction. So 28,000 equals 7,000 plus the normal force. That gives us a normal force of 21,000 newtons. So those are the two forces. All right, so that's pretty much all of the calculation that there is for this problem. There's one last question. Part D asks us, now if there is friction between the cart and the loop, then what could be done to modify the loop or the track in general so that the cart will have the same speed at the top of the loop as what we calculated in part B. So if we look at this, friction would cause the cart to slow down as it goes, so it would not quite have enough speed at point B. So one thing we can do is we can drop the top of the loop like this. If we do that, then the cart will have less gravitational potential energy, so there will be more kinetic energy. Other things you could do to prevent the cart from falling out of the loop, if that's what you're worried about, would be to change the radius of the loop, but this question specifically says that we want to maintain the same speed at the top of the loop, so we do need to bring the top of the loop closer to the ground, and that's our answer there. Great, so let me throw in one last sort of extra element to this problem. What if we were asked the minimum speed that the cart needs to have at part B to make it through the loop? Or a related question, how high must the hill at point A be in order for the cart to safely make it through that loop? So I won't go all the way through this problem and get the final answer, but I will at least mention how that problem would be approached. So the idea here comes down to this free body diagram that we drew. As the speed of the cart changes, this normal force will either increase or decrease. And remember, when the normal force becomes equal to 0, that means there's no longer contact between the cart and the track, so the cart would fall off. So if we want to find that point where the cart is just about ready to fall off the track, then what we would do is set the normal force equal to 0, and then that leaves us with an equation that says the net force, mv squared over r, would be equal to just the gravitational force. So if we solve this, this tells us the minimum speed required to make it through the loop. Then if we know the minimum speed that the cart needs at point B, we can calculate how much kinetic energy the cart would have at that point. We could also calculate how much gravitational potential energy it needs at that point, or how much gravitational energy it would have at that point just by looking at the 50-meter height. And we could then find out how much total mechanical energy the cart would have at point B, and we could set that equal to the total energy at part A and figure out what the height of the loop would need to be. All right, so that's if you're wanting something a little bit extra to try, see if you can figure out the answer to that part. All right, so as always, feel free to message me if you have any other questions about this problem. Thanks, and have a great day.